Session hijacking refers to a class of attacks that target the state tracking data associated with a client-server session. State information consists of anything persistently stored by the server over the duration of a session, such as the username of a client or the contents of an online shopping cart. Tracking data associated with state allows a server to associate multiple client requests as belonging to a single session. What data is actually used to track session state is protocol dependent, and even within a protocol, different types of data can be used depending on the implementation. Flaws in the protocol itself can be leveraged by an attacker to steal or guess state information associated with a target, and thereby inject the attacker into the session in one form or another. Typically, this is done after the legitimate client authenticates with the server, thereby enabling the attacker to masquerade as an authenticated client. Such attacks can consequently be classified as authentication bypass attacks, since they let the attacker access a resource without having to compromise the authentication function itself. What permits session hijacking to occur are various vulnerabilities that, in one way or another, allow an attacker to obtain a session variable. Here we consider 4 vulnerabilities. The first type of vulnerability permits session data to be predicted. An example of this is TCP sequence number prediction. Sequence numbers, along with IP addresses, are used by TCP to track sessions. In early versions of TCP, sequence numbers were incremented by a predictable amount every second. By making a normal connection to a server, an attacker could determine the current state of the sequence number generator, and thus predict its likely state in the near future. The attacker could then send malicious traffic to the server with an IP spoofed to that of a trusted host. However, the attacker faced the obstacle of completing the TCP three-way handshake, which requires knowledge of the sequence numbers used in the traffic sent to the client by the server. Since the attacker's traffic was spoofed, the attacker had no direct way to see the sequence numbers returned, hence the need to predict them. If an attacker successfully manages this form of blind handshaking with the server, commands could be sent to be executed on the server due to the fact that the spoofed IP represents a trusted client. That is to say, one not requiring any authentication. This is a challenging attack, not only due to the imprecise nature of predicting sequence numbers, but also due to the fact that the legitimate client whose IP was spoofed may respond to the unexpected traffic from the server with TCP reset packets, thereby closing the attacker's connection before malicious data can be sent. Another type of vulnerability permits session data to be obtained by direct observation due to the lack of controls ensuring confidentiality. An example of this is network sniffing to obtain HTTP cookies. I'll discuss this in more detail in the next slide, which focuses on web application session tracking. A third type of vulnerability is one allowing the attacker to choose session state and give it to the victim, which the attacker then uses after the victim authenticates. This type of attack is called session fixation. It can be accomplished in the form of a URL that encodes the attacker's chosen session ID. Such a malicious URL can be delivered in the form of a standard social engineering attack. Success of this attack, however, requires a target web application that does not change the session ID after the legitimate user authenticates after visiting the URL. All the attacker has to do here is deliver the malicious URL and wait for the user to authenticate, after which the attacker can reuse the known session ID to masquerade as the authenticated user. The last category of vulnerability I consider here is vulnerabilities that permit outright theft of session data. An example of this is cross-site scripting attacks, which allow attackers to circumvent the same origin policy that would otherwise prevent their access to cookies. This policy only allows client-side scripts to run if they originate at the same site as the current page. A malicious script can steal session data in the form of cookies, but due to the protection provided by the same origin policy, the attacker has to find a mechanism to have the malicious script be delivered to the client by the trusted web server. One mechanism to do this involves message boards that allow HTML markup in the message text. Malicious script code embedded in this manner may not be visible to the victim after reading such a message, but will execute in their browser while they are logged into the message board site, typically sending their session information, username, real name, or other available information back to the attacker. Here I want to discuss session tracking with web applications because this is such a commonly encountered context for sessions. 3 general mechanisms are used to track session state in web applications. The first mechanism is URL encoding. In this method, session data is encoded as parameters in an HTTP GET request for data going to the server, and as parameters in URLs returned to the client. Another mechanism is hidden form fields. Although forms are typically used for user input, they can also be pre-populated with data by the server in the response it sends back. If the fields are tagged as hidden, they will not be displayed by the client browser, and the user will be unaware of this data being passed back and forth. The third mechanism is HTTP cookies. Cookies are data sent to the browser as part of the HTTP header. The client browser is supposed to pass them back unaltered to the server, allowing the server to track session state. Cookies can be marked as secure, meaning that they should only be passed in HTTPS, and they can be given expiration dates, including immediate expiration, meaning that they are non-persistent, that is, stored only in memory and vanishing after the browser is closed. Vulnerable web sessions can be hijacked by an attacker via the methods previously mentioned, such as cross-site scripting, session fixation, and sniffing. Cookies, for example, can be obtained via sniffing when transmitted via HTTP as opposed to HTTPS, and subsequently reused by the attacker to imitate the target user. Please see the session hijacking demonstration video for an example of this type of attack conducted against Amazon.com.